Let's look at how to solve an example problem in conservation of momentum in 2 dimensions. So what we're going to do is we're going to say we have a ball that has mass m, and it's going to strike another ball that has mass 3m. Okay? They're going to have a perfectly elastic collision, and as a result of that collision, ball m is going to deviate from its original path by 90 degrees, and it's going to end up going this way. Okay? Because momentum has to be conserved, we know that the ball that has mass 3m has to have a component in the positive y direction, because the net momentum in y has to add back up to 0, and it has to have a component in the positive x direction because, again, this thing had some initial momentum in x, and that has to be carried forward. So let's say that this had an initial velocity of 2 meters per second. What I want to know is, what are the final velocities of both of these balls after the collision? And remember, it is an elastic collision. Now, to do this problem, I think it helps to actually have a diagram of what's going on. We need to remember that momentum is conserved, and conservation of momentum means that the initial momentum has to equal the sum of the final momentum, or the sum of the initial momentum, but I only have one momentum initially. Initially, I have a ball that has a mass of m, and it's moving with velocity 2 meters per second. So it has an initial momentum of that. Okay? Now that means the final momentum has to add up to that. Well, the final momentum is this ball of mass m moving straight down. So I'm going to put that right here. Okay? So this is afterwards. This is m, and it has some velocity va for ball A. And our second momentum is from the other ball, and it has to add up to what we started with. So this is 3m times vb. So what I have is this momentum afterwards plus this momentum afterwards is equal to the momentum that we had to start with. Now I can also write that out in terms of its components, right? I can say that initial momentum, and it is in 2 dimensions, so I have to keep it in 2 dimensions. The initial momentum in x is the final momentum in x, and the momentum in x originally was m times 2. This has to equal the momentum in x finally. The VA doesn't contribute to that at all, but VB does, and so I can say this is equal to 3m times VB, but not all of VB, only the section of VB that is in the x direction. And I can actually dash in a component to that down here if I'd like. And so this would be the angle theta, and I could say this would be times the cosine of that angle. That would give me the x component. Similarly, in y, I can say the momentum in y, which was 0 initially, has to be 0 at the end, and this would be 3m vb times the sine of theta plus mva. But I also have that this is a perfectly elastic collision, and because it's a perfectly elastic collision, I can write the law of conservation of kinetic energy there. And so the kinetic energy that we have at the beginning is equal to 1/2 of m times 2 squared, and this has to equal the kinetic energy at the end. Now remember, kinetic energy is not a vector. I don't have to care about its dimension or its direction. All I care about is the 2 objects that are in motion. So I have 1/2 of m times va squared plus 1/2 of 3m times vb squared. Now, with these, it's not maybe intuitively obvious where to go, but I think if we look at the picture of the conservation of momentum and we realize this is a right triangle, we can use Pythagorean's theorem to eliminate some stuff. Otherwise, we're going to do a lot of substitution to eliminate stuff. Either way, you're going to end up using quite a bit of algebra to solve this problem. So what I want to do is I want to concentrate on solving this problem with our conservation of momentum. According to the law of conservation of momentum, we have these two, the final momenta, add up to the initial momenta. And I'm going to go ahead and write that in terms of the Pythagorean theorem, because to add these vectors at right angles, I can do that. I can say that m2, not m2, but m times 2 quantity squared plus m times VA, quantity squared, right? This is the Pythagorean theorem, is equal to 3m VB quantity squared. Now, in every single one of those terms is an m. I'm going to divide it out. It doesn't matter. So this becomes 2 squared, which is 4, plus VA squared equals 3 squared, which is 9, VB squared. And like I said, I divided out the m's because I can. It makes the math easier. So this is one equation, but that one equation has 2 unknowns in it. And if I have 2 unknowns, that means I need another equation. Well, I already have that other equation. That equation is written right here with the law of conservation of energy in terms of an elastic collision. We have the kinetic energy. In each one of these terms, there is a half m. So I'm going to divide the half m out, and I'm just going to write what's left over. And so this equation simplifies to 2 squared is 4. 4 equals VA squared plus 3m, but the m is gone, and VB squared. Okay, so now I have this other equation. I have this equation that has VA squared in it and VB squared in it, and I have this equation that has VA squared in it and VB squared in it. And so I'm going to go ahead and just solve this equation for VA squared and get VA squared is equal to 4 minus 3 VB squared. And then I can plug that in to this equation. So I'm going to have 4 plus 4 minus 3VB squared, right? So this right here just took the place of that VA, is equal to 9VB squared. And when I add that over, I have 8 is equal to 12 VB squared. You can divide both sides by 12, and what I see is VB squared is equal to 2 over 3, and I can square root both sides of that and get VB equals the square root of 2/3. Okay? That gives me enough information to find VA, because now I can substitute VA or this into this equation to find VA. So I get VA is equal to, or VA squared is equal to 4 minus 3 times VB squared, which would be 2/3. The 3 cancels, and I get VA squared is equal to 4 minus 2, which is 2, or VA is equal to the square root of 2. Of course, this would be meters per second. This would also be meters per second. Now, the only thing left to do is find the angle. But I can do that because back over in this triangle, clear over here, I now know values for VA. I know a value for VB. And so I know the sides of my triangle, and I can find this angle. It's the same as this angle. And so I would say theta is equal to the tangent, the arctangent of, and again I can ignore the m's on this equation. I would say VA, which I know is the square root of 2, over 2. And now I have my angle as well.